Okay, today I'm going to be talking about z-scores. This refers to Chapter 5 in your textbook. It's going to become real clear in this talk why you need to understand the standard deviation from the last chapter, because where this chapter gets difficult, it's mostly in linking z-scores back with standard deviation. So if you understand standard deviation pretty well, it'll make this go a lot smoother. Alright, first let's talk about why do we use z-scores. So what are z-scores and why would we use them? But before we do that, let's stop and take a look at where we are relative to the other topics in the class. So we started with descriptive statistics, frequency distributions, mean, median, mode, and all that. Next we're going to inferential statistics. The first introduction to inferential statistics that we're going to see is a test using z-scores, and then later we're going to build on that and get more complex to other tests in the class. So we're right at the edge of the z-score technique we're going to be learning in this lecture is a descriptive technique, but we're going to use it to kind of transition into inferential statistics. So just keep track of where we are. Z-scores are an easy way to look at distributions. In order to understand z-scores and to perform in this chapter, we're going to need to understand the mean and the standard deviation. We're going to need a little bit of algebra, but that'll become self-explanatory. So why are we using z-scores rather than using standard deviation? Well, here we are. So the first thing that we need is to define what a z-score is. So we're going to create a z-score that's going to be equal to a raw score minus the mean. Remember, this little symbol is mu, it stands for the mean, divided by the standard deviation. So this is where we need to know what a raw score is. We need to know the mean and the standard deviation of a distribution. Remember, when we're talking about raw scores, these are just scores that we're given, like that we'll find on a frequency distribution table. Maybe it could be literally scores that somebody receives on a test. Could be any dependent variable that we measure. Could be severity of reaction to a medicine. Could be IQ scores. Could be anything. So let's say we have people's real scores, and somebody makes a score of 115 on an IQ test. The reason I like it, the reason I like the example of IQ is that for IQ, it's very easy to remember. The mean of the distribution when we're dealing with IQ is always 100. It's defined that way. And then the standard deviation of the IQ distribution is always 15. So if somebody receives a score of 115 on an IQ test, that means they have a z-score on that test of 1. Now, hopefully it'll be easy to see at this point. Let's graph a distribution of IQ scores. It's not the best graph, but it'll work. And right here's the mean. Like I said, the mean is 100. And here is our score. Somebody scored 115. Alright, here's why understanding standard deviation is very important. You'll notice that our score of 115 is exactly one z-score above the mean for this distribution. Our standard deviation is 15. So 15 equals standard deviation. Our guy scored a 115, is exactly one standard deviation above the mean, and he was assigned, when we calculated the z-score, a z-score of 1. Z-scores are an easy way of telling us somebody's score in standard deviations. So somebody that scores 1 standard deviation above the mean has a z-score of 1. If I score 1 3/4 standard deviations above the mean, then my z-score is going to be 1 3/4. So z-scores are just a quick and easy way to let the reader know that you're talking about units of standard deviation. And as we're going to see throughout the class, a lot of times giving someone the information, this participant scored a 115, doesn't provide much information. But telling the reader this participant scored, had a z-score of 1, automatically conveys several pieces of information, like how well they did relative to the mean of the distribution, the standard deviation of the distribution. Okay. The most important thing about z-scores is that they allow comparing different distributions. Being 1 standard deviation above the mean can mean different numbers for every distribution, but being 1 standard deviation above the mean always corresponds to a z-score of 1, exactly 1. We'll go through some examples in a minute to put this into context. So just a real quick review of distributions. We can say different descriptions of distributions. One is, what is the shape of a distribution? We talked about symmetrical distributions, skewed distributions, we mentioned bimodal and some other things. We can also talk about the central tendency of a distribution, where the mean, the median, and the mode are, for example. We can also talk about the variability of a distribution. Variability is the degree to which scores in a distribution are spread out or clustered together. Variability is the degree to which scores in a distribution are spread out or clustered together. So this is how we can describe distributions kind of generally. We've mentioned before the normal distribution. The normal distribution is a hypothetical distribution that has exactly the same shape every time. It is a distribution in which the mean, the median, and the mode are all exactly the same value and are all the point of symmetry for the distribution. So they're exactly in the middle. Okay. Just probabilistically speaking, if I randomly choose a score from a normal distribution, if I choose a score at random, it is most likely to be the mean. We can illustrate this really quickly. Why is that important? What are we talking about? Okay, here is a very poorly drawn normal distribution. You can look in your textbook for an example that is not drawn terribly. So here's a normal distribution. Because the mean, median, and the mode are all in the center of the normal distribution at the point of symmetry, if we randomly pick, let's say we randomly draw a dot somewhere on this distribution. I'm going to wave my mouse around and randomly click. There is a very small chance that we will randomly draw a score from this section of the distribution. There are just more scores here in the center of the distribution, so there's a higher probability that we'll choose a score somewhere toward the middle of the distribution. Remember, the height of this distribution shows us how many scores are there. So it's more likely we will get a score from the body of the distribution than it is we'll choose a score from the tails. But it is most likely that we will choose a score exactly equal to the mean. There's not a much higher probability of choosing this score than there is, say, this score that's just off center. But still, statistically speaking, it's most likely we'll hit a score exactly equal to the mean. We can rephrase this question and say, when we randomly choose a score, how close would that score be to the mean? It is most likely that a score that we randomly choose will be within 1 standard deviation of the mean. It is most likely that a score we randomly choose will be within 1 standard deviation of the mean. So how do we use that information? Consider a score of 11. Using this graph right here, would a score of 11 be considered a typical score that would be likely to find? So is it within 1 or 2 standard deviations of the mean? Let's add some numbers. So what do you think about a score of 11? If we say the score is typical, if it's within 2 standard deviations of the mean, would a score of 11 be considered typical? Using these numbers, you can pause and try to get the answer for yourself for a second. But now using these numbers, a score of 11 falls way outside of the range of 2 standard deviations. Numbers are kind of cut off here, but a score of 9, using this mean and standard deviation, is a cutoff point for 2 standard deviations. So a score of 11 is way far out here. It's very unlikely that we would randomly pick a score of 11. But let's change the mean and standard deviation. The mean is now 10, and the standard deviation is also 10. Now, where would a score of 11 fall using this new set of scores? Score of 11 is going to fall right here, right beside of 10, and is going to be a very typical score of this distribution. Alright, see right here where we get a lot of information just from the standard deviation, which, remember, also corresponds to z-scores. A score of 55 in this distribution right here would correspond with a z-score of 1, for example. Okay, so how else are we going to utilize z-scores? So in the situation in which we want to use z-scores, the thing that we want to do is identify exactly where a score lies in the distribution. One simple question we could ask is a score in the body or the tail of a distribution? This is the same thing as saying, is a score typical of a distribution, or is it an extreme score, an outlier? For right now, we're going to call scores that fall somewhere outside of 2 standard deviations from the mean an extreme score. We're going to make it a little more specific later in the class, but in general that's a good cutoff point. So if a score is outside of 2 standard deviations, we're going to call it an extreme score. So like I was saying earlier, the raw score, or the X value, stands for score, provides little information comparing a score to other scores in a distribution. For example, if I told you that someone scored a 53 on an exam, without giving you any other information, a score of 53 on an exam could be a relatively low score, it could be average, or it could be high. Just given that information, there's no way to tell. If you're given a z-score, however, you know something with a z-score of positive 2 on an exam was on the high end of scores for the exam. Something with a z-score of negative 3 on an exam means that that person scored particularly low compared to others in the class. Let's go through this example. This is one of my favorite examples to show the utility of z-scores. Let's say these are 2 different classes. So I'm taking 2 different classes this semester, and I have 2 tests on the same day. And on the first test, I score 25 points. And on the second test, I make a 46. So on which of these tests did I perform better? And the answer is, just given this information, so you don't know the possible points for either one of these tests. Right now, we have no idea which test I performed better on. But if we transform the raw score into a z-score, this tells us exactly where the scores on the test are relative to other scores. So the z-score gives us two pieces of information. One is the sign of the z-score can either be, the z-score is either going to be 0 or it's going to be positive or negative. A z-score of 0, by the way, corresponds to a score that is exactly equal to the mean. A z-score of 0 corresponds to a score that is exactly equal to the mean, which will be important in later discussions. If a z-score is positive, that means that the raw score it corresponds to is above the mean. A z-score that is negative means that the score is below the mean. The second piece of information a z-score gives us is through the numerical value. The numerical value of the z-score tells us how many standard deviations away from the mean the raw score is. Like before, a z-score of -1, for example, tells us that the score we are interested in is 1 standard deviation below the mean. A note here about vocabulary. Remember the difference between a statistic and a parameter. Z-scores are calculated, but they are not statistics. Z-scores are something called transformed scores. Transformed scores are when you take the raw scores in a distribution and perform the same mathematical operation on every score. It's not going to be so important for the tests that we're performing in this class. We're going to try to stay away from transforming scores. But in statistics in general and in more advanced classes, transforming scores is a good way to take a distribution that is unanalyzable and turn it into something that is easy to perform statistics on. But right now, let's focus on just z-scores and non-transformed scores the rest of the class. Okay, so a couple of examples here. A z-score that is 2 standard deviations above the mean will have a z-score of +2. So just some more examples. Okay, so this is an example from your book, but I actually think that so you can look at this slide and you can look at this in the book, but I actually don't think it is illustrating the point as clearly as this will be able to. When we are looking at a distribution of scores, let's say here's a distribution of scores, and we know that the mean, so this is a population because I'm using the mean symbol for population. Let's say the mean of this population is equal to 54. So right now I am, and let's say this is a test. The mean on the test is a 54, and well, I probably score over here on the low end. Let's say that I scored a 36 on this test, and 36 just happens to be 1 standard deviation below the mean. So doing that math in my head real quick, that means the standard deviation for this distribution is equal to 18. So all this that we're looking at, I'll draw it in blue. This is a distribution of raw scores. Now here's what the illustration from the book was trying to show us. Let's say that we don't want to deal with raw scores anymore. We want to deal with z-scores. Thing is, the distribution itself doesn't change. None of these numbers that we've already dealt with change. We can graph the z-scores right alongside the raw scores. A z-score of 0 corresponds to the mean. The z-score over here is going to be -1 because that's 1 standard deviation below the mean. The standard deviation of a distribution of z-scores is exactly equal to 1. But we're not dealing with different scores. I'm not even going to redraw the distribution here. Transformed scores, the numbers for the standard deviation, the mean, and these scores here, the numbers all change, but we're not dealing with a different distribution. We're dealing with the exact same numbers, we're just labeling them differently. That is the benefit of using z-scores in this context. So that'll become, it's important for your homework questions, it's important for this chapter conceptually. Here's another illustration of this principle. So we have a distribution at the top of the slide in which the mean starts at 100. We have a standard deviation of 10. We could just as well label with the z-scores and have a mean of 0 and a z-score, or a standard deviation of 1. The z-score distribution will always have a mean of 0 and a standard deviation of 1. I'm probably repeating that point throughout the lecture, but it's an important point, so I think it bears repeating a little bit. Okay, so let's go back to how do we actually convert. So what I did on that slide was convert a distribution of raw scores to a distribution of z-scores. This process that is outlined on the slide right here is not only the way to transform one score from a raw score to a z-score, but this can also be done on an entire distribution of scores. The examples we've seen in previous slides using distributions were examples of that, where this formula was applied to every score in a distribution to turn it from a raw score distribution to a z-score distribution. Let's go through a couple more examples just to make sure everybody's following along. If we have a raw score of 3, what would the z-score be equal to? That's correct. Plug it into this formula, and we end up with a z-score of -1 for a raw score of 3 for this distribution. Okay. Going through another example, if we have a raw score of 8, we just plug that into the formula and get a z-score of 1.5. Like in this example, a z-score of 1.5 tells us that the raw score of 8 is 1.5 standard deviations above the mean. That's weird. Okay, let's go back to that example before. Let's say I took 2 tests in a day. I made a 25 on the first test and a 46 on the second test. At first glance, it might look like I did better in the second class, making a 46. But what if we add information about the mean score for each of those classes? And next, we add information about the standard deviation for both of those classes. In this case, I made a better score than the mean for both classes, but using z-scores, see if you can determine which score is the better score objectively. Alright, so I'll give you a second to pause the video. Here's the answer. So on the first test, I was actually 2 standard deviations above the mean. And on the second test, I was 1.5 standard deviations above the mean. Both of them are positive z-scores, are still above the mean, but the score of 25 was better relative to the class. So this is a practical application of z-scores. We'll skip that for now. What if we want to go the opposite direction? What if we have z-scores and we want to find out the corresponding raw score when we have a z-score? This is a common occurrence because things will be reported in z-scores, but you're really interested in the raw score. There is an easy transformation. You'll notice, take a second to look that this formula algebraically is the identical formula to the z-score formula we saw before. It's just rearranged a little bit algebraically. So utilizing the new rearranged formula, if we know the z-score is 1 and we have the mean and standard deviation here, what is the raw score for a z-score of 1? Well, we apply the rearranged formula and we come up with a raw score of 7. Okay, pause a second to do this next example. We have a z-score of -2.5. What is the corresponding raw score? And again, we just apply the formula and we find that the corresponding raw score for a z-score of -2.5 is 0. Notice that as long as we have at least 3 pieces of information, we can rearrange the equation to find the 4th piece of information. What we started out doing is having the mean and standard deviation. We used a raw score to find the z-score. In the last couple examples, we still had the mean and standard deviation, and we used a z-score to find a raw score. So having 3 pieces of information, we find the 4th one. This can be done for mean and standard deviation just as easily as it was done for raw scores and z-scores. Now, let's compare the distribution for the raw scores to the distribution of the z-scores. If the shape of the raw scores is normal, remember, the shape of the z-scores is the exact same as the shape of the raw scores. It doesn't change the shape of the distribution. Now, the measures of central tendency, for example, the mean for a distribution of raw scores, can be a lot of different values. It could be a mean of 30, a mean of 40, a mean of 100. But the mean of the z-scores will always be 0. The standard deviation of a set of raw scores can be anything. It can be 1.5. It can be 0.705. It can be anything. The standard deviation of a set of z-scores is always equal to 1. It's defined that way. Now, let's look at this example for a minute. Just want to point out that the scores on the top and bottom of the slide represent the exact same distribution, but we have transformed the distribution at the top into a set of z-scores at the bottom. We're illustrating here the 3 points from the slide before. The first important point is that the distributions are the exact same. The second point is that the mean of any distribution, any raw scores, is equal to 0 in z-scores. And the third is that the standard deviation for any distribution, when transformed into z-scores, will be equal to 1. Alright, those are 3 important points. So it's useful, in addition to knowing the basic definition of a z-score and the formula for z-scores, it is useful to be able to visualize z-scores as locations in a distribution. So remember that z equal to 0 was always the mean of a distribution, always at the exact center. And the extreme tails of a distribution always correspond to anything that is beyond 2 standard deviations from the mean, or beyond z-scores of 2. So that means above a positive 2 z-score and below a negative 2 z-score. Most of any distribution is contained within negative 2 and positive 2. Just to illustrate this again, this is a distribution. We're going to consider an extreme score. That's supposed to be a 2. We're going to consider an extreme score anything that falls either above positive 2 or below negative 2. So any raw scores that fall over here or above here be considered extreme scores. That's what the slide is talking about. So the advantages of z-scores is that we are standardizing distributions so that different distributions can be made the same, so that they can be analyzed using the same numbers, which are z-scores. So we can compare two distributions that might not have any characteristics in common otherwise. But z-score distributions do have something in common. Even if they come from wildly different sets of numbers, all z-score distributions will still all have the same mean and standard deviation. Now, in the examples before, we have been calculating z-scores for populations. It is also possible to calculate z-scores for samples. Make sure to review the difference between samples and populations. The definition of the z-score for a sample is the same, except we are using the sample mean and sample standard deviation instead of the population mean and population standard deviation. Remember, this formula reads z equals the score minus the mean of a sample divided by the standard deviation of a sample. So we don't have to change the formula. We can do the same thing with samples. Really, the only thing that changes is in the calculation of the standard deviation that is used in the z-score equation. But the z-score equation itself has no changes. So remember that the calculation of the standard deviation uses n minus 1 instead of just using n when we are dealing with a sample. Okay. So z-scores, I've been singing their praises through this presentation, have a lot of uses, and we'll make use of them more in the next chapter. But z-scores can be somewhat burdensome. One way is when z-scores have different decimal places. They're harder to read. All the examples we've been using have been like a z-score of 1 or 1.5. So, are there anything that could be simpler than z-scores? And the answer is most often z-scores are enough. But one example that we're going to take from the homework assignment is when we are creating a different standardized distribution based on z-scores. And how we do this is step 1, we need to select the mean and standard deviation we would like for the new distribution. So we use z-scores to identify each person's position in the original distribution and compute their position in the new distribution. And how we do this is step 1, we take all the raw scores from the distribution and transform them to z-scores. Let me write this out. So step 1, convert to z. I know that the textbook I'm using right now has a few questions like this. The very last couple questions I've assigned, so it'll make sense when you come there. So step 1 is convert to z-scores. And step 2 is use the second formula that we learned and plug in our new z-scores step 2, once we have converted our scores to z-scores, step 2 is to use the new mean and standard deviation that we have selected. So we will use a new mean and standard deviation that we have selected with the z-scores we calculated in order to calculate new x scores, new raw scores. Okay, so that process sounds confusing. So let's go through an example. Let's start here. So if our goal is to convert a sample distribution of scores to a new distribution, we want our new distribution to have a mean of 10 and a standard deviation of 2. But we know that our original distribution had a mean of about 108 and a standard deviation of about 16. If a participant had a PFC score of a raw score of 101.52 in the original distribution, what is their new score? Step 1, convert their raw score to a z-score using the original mean and standard deviation. And step 2, convert that z-score to the new raw score using the new mean and standard deviation that we selected in the slide a minute ago. So this last step corresponds to a couple homework questions and might be a little confusing. Make sure to post about it on the forums. Make sure to keep in touch with me, and thank you.